Why don't you all pass your exams in towards the center, and I'll just come on through and pick them up in just a moment. Okay, folks, are there, if I can get everybody's attention, are there any exams still out there that I haven't picked up yet? All right, cool. Hope you found the exam to be something that was quite manageable. There was a number of folks that did reach out asking good questions, and that went for your class as well as the 335 class. I appreciate those questions, folks. If you were among those that reached out and asked questions, and hopefully those questions helped you. The one thing you may have noticed about the questions and the answers that I gave to the questions, it wasn't, rarely do I just directly answer a question. It's more of, I want to teach you. So if you didn't know the answer to something, okay, here's the way you need to think about it, or look at this, for example. There were some questions like, well, hey, how do I represent a pin forces? It's like, boy, we talked about that one a couple of times. So in that case, I'm not just going to come and answer. I'm going to say, hey, refer back to, because that's where your answer is going to be found. So I think what I'm going to do is not really spend any time talking about it this morning until I've had time to look over yours as well as the folks from the 335 section, and I'll get these assessed or evaluated, graded, and get them back to you here. Hopefully, probably by about Monday. That'd be my game plan at least, and we'll talk about it then. Did anybody though before we put a pin in the midterm exam? Have you got your midterm to turn in?
Yeah.
Okay. Does anybody have any questions about it that you want me to answer now? Anything at all, anybody? Thank you very much. All right, well, hearing none. So, folks, I want you to realize, too, a couple things. It's odd to call a midterm when we're having it so late in the semester, and I want you to make sure we all understand this belies my fundamental approach of the course, actually all courses I teach, in that it's not about when we take the exam, it's when we're ready to take the exam. And in this case here, there's no sense in giving you any kind of exam until we're at the point where we are evaluating the fundamental outcomes, the fundamental learnings of the course. In other words, if we don't evaluate what it is you need to know coming out of this course in a first evaluation, then what's the point, right? It doesn't tell us anything. So we have this midterm late. I don't know if it concerns anybody in here. My guess is it shouldn't concern anybody in here, but there's always the question that pops up of, well, it's so late, we're so close to drop ed, what if I don't do well? This is simple. If you don't do well, let's fix that problem. Yeah, I literally had people not do well on a midterm and go and drop the course without telling me they were going to drop the course. It's like, what the fuck are you doing? Because it's not going to get easier the second time around. Let's fix the problem now. So, and I'm saying all this to say, and I won't know it until I see this, of course, right? But if anybody had problems or struggled with this here, it doesn't matter that we're doing it late in the semester. What matters is that if there was a challenge, if there was problems, we will fix that and get it right before the end of the semester. That's the play here, folks. It's not about, gee, I need to start over. You never do. Okay, so if nobody has any questions about this, all right, fine. Let's talk about Chapter 5. And by the way, Chapter 5, Chapter 6 will be the last chapters that we'll cover in the course. It is going to go fast, and there's going to be information in these chapters that, well, let's put it this way. The primary focus of the final examination will be Chapters 5 and Chapter 6, very much like we did with the first one. There will be probably 3 questions devoted to those 2 chapters, and man, like I say, it's going to go really quick. So my strong encouragement to you all is this, and I want to make sure everybody's hearing me crystal clear when I say this because it's important. We really did, by design, take our time to get to the midterm, to make sure we really built the foundational stuff to get everybody to the point where, yeah, you're ready to take that midterm. It doesn't work that way now that we're on the second, the second half of this, or the second fraction of this course here. This one's going to go fast. You can't get behind. We're going to have the final, by the way, done before we get to the finals week, so I want you all to know that. We're not going to wait till then to get that under our belts. So this is going to go quickly, and my strong advice to you is if you're not keeping up, or if there's not a, there's something that we're talking about that's like not clicking, do not wait until the end to address it. Otherwise, you are putting yourself at peril. Point being, that right now with the midterm, and again, I'm speaking purely hypothetically, if somebody had a problem with the midterm and didn't do well in the midterm, we're gonna fix that. We don't have that luxury after the final. So if you don't do well in the final, there's nothing we can do about it, it's over with. So I want you to have that in your mind as we talk now about Chapter 5. Go ahead and Chapter 5, folks. Chapter 5 and Chapter 6 both are really just filling in some of the holes of things that we've been ignoring from minute number 1. In Chapter 5, there are 2 fundamental things that we are going to learn, and they really are illustrated in what you see up here on the board. I want you to take a look at the beam that we have on the board right here, folks. Until today, or in other words, before now, if we represented a force acting on any kind of a mechanical system, I'm just using the beam here as purely an example. I've got a beam in the nothing's new here department, folks. The beam is supported by a pin, it's supported by a roller. We all know what those things are, what they look like. Before today, if I represented a force on this beam or any other mechanical system, we've all seen it. It's a single point concentrated force. It's a single arrow pointing someplace, applied someplace on that beam. We would probably have dimensions and stuff telling us about where it is and all that kind of stuff. And right now, for example, if I told you that, hey, this force right here is, let's just say it's 100 pounds. This force is 100 pounds, and the force is, let's say this is a 10-foot beam, and let's just say, even though it looks like it's right smack in the middle, let's just say that this is 4 feet over from the pin here at this side. If we knew 100 pounds, 4 feet from here, and we know the overall length of this beam, and I want you to, if you don't do it physically, at least do it mentally, nod your head if you agree with what I'm about to say here. Nobody in this room right now should not be let me say that differently, so I'm doing double negative. Everybody in this room right now should be able to figure out what the forces are on this pin and what the forces are on that roller based on stuff we already know. In other words, we know how to do this problem. Again, if you weren't able to mentally nod your head like, yeah, I know how to do that, all right, fix that. Now's the time to fix that, folks. So that's where we were before today. Now, finally, we're going to stop ignoring a fundamental fact that I've talked about a few times already in the course, the idea being that real-life forces, they're not arrows. We don't have, for example, I'm standing on the floor right now. The force of my weight is not an arrow pointing at the floor. It is a force that's distributed over a certain amount of area. In this case here, it's the area that comprises the bottom of my shoes, is what it boils down to, right? If I sit down on this table right here, guess what the area is that's going to be that my force is going to be distributed over? It's going to be the print of my you-know-what, right? It's over a real area. If I had, for example, if I had an aquarium here, I've got an aquarium, like a fish tank, sitting right here on top of this tabletop right here, and I fill this thing up with water. So I don't know, let's say it's a 30-gallon tank, right? What's a gallon of water weigh? About, I don't know, 10, 11 pounds, something like that. I honestly don't know. I knew this at one time. Let's just say it's 10 pounds to make our math easy. So I've got 30 gallons of water, about 10 pounds a gallon, sitting in this aquarium. that means there's 300 pounds pushing down on this table. Now, is that 300 pounds a single point like right there? Is it a single point like right there? Or is it distributed over the area that's in contact with the table? Common sense tells us it's over the area that's in contact with the table. Now, that's real life forces. Yet we're still not quite operating in real life now, are we, folks? Because we're still living in 2D statics. So even though we all can envision what an aquarium filled with water looks like, right? But we're living in 2D world. 2D world like up on the whiteboard right here. So even though the reality of that force is it's distributed over an area, if we're living in 2D world, the reality is that force is distributed over a line, a plane, right? An XY plane. We're moving in a direction where we're going to contemplate that. We're going to represent those forces as you're seeing right here, where instead of the force being visually represented as a single arrow, now we're representing that as some sort of a continuum with a bunch of arrows coming down and resting, or not resting is a better way to say it would be articulating with a finite distance here on our XY plane. And you'll notice the way that I drew this. Looks to me like the height of this arrow here is a little bit taller than the height of this arrow down here. Is that meaningful? Yeah. What that means is, and here's the voice of common sense speaking in our ear one more time, that means the longer arrow has more magnitude to it than the one that's shorter. So if you imagine, again, my aquarium filled with water right here. If the aquarium is sitting flat, and I got this filled up with water, then the water is flat to or horizontal to this plane down here, right? That means that if I took out a column of water over here and a column of water over here, those columns would both weigh the same. But what would happen if, on the other hand, I turn the table upwards on an incline right now? So I got way more water down here than I got water up here. I pull out, let's say I've got only a column that high up here. I pull out a column like that. Down here I got a column this high. I pull out that column. Do I have more weight in this column than I got in this column over here? Well, obviously I do. So in this case here, this distributed load, the way you can see this distributed load would be to say, oh, okay, well, in this distribution of forces, I've got more here, less here, and the relationship between these two extremes is linear. This is a common representation for a distributed load. As we're going to see, there's all kinds of different ways that we can represent distributed loads. The question, though, comes to this. Did you have a question back there?
Yeah, so with like a distributed load, are you just effectively taking, like I said, say it's a object a foot long, are you just going to take a measurement of the force at like every inch or every other inch and have it move along the object that it's sitting at, right? Or are you just kind of splitting it up into those component parts, or?
Yeah, the answer is, to like part A of your question, not really, and then part B of your question, yeah, kind of like that. And we're going to get to that, all right, we're going to get to that. But yeah, you're already thinking, okay, fine, how do I deal with this, right? How do we deal with this? And this is the good news, folks. So if this is where we were before this morning, and this is where we are now, the question is how do we deal with it? What's our goal and strategy? And to your good question, what's the play here? The play, folks, and you're going to love this, the play is real simple. We're going to learn how to convert that into that. And once we convert that into that, we already know how to do that. In other words, we're going to do nothing more than convert, we're going to learn how to convert a distributed load into its equivalent single point load. In other words, an equivalent force system. And what have we said from day one about equivalent force systems? Equivalent force systems are those systems that give us the exact same effect on the mechanical system. In other words, if we properly do this, if we convert this into this correctly, then the solution for this, if we want to know, for example, what's the force on the pin here, what's the force on the roller right here, the solution to this would be exactly the same as the solution to that. Problem solved. So for us, this gets nice and easy. All we need to figure out how to do is answer two questions. If I have this and I want to go to this, then question number one, what's the magnitude of this have to be? What does the magnitude of this need to be in order to be equivalent? And number two, importantly, where do I put it? Should I put this arrow like right there, or should it be here, or maybe just a little bit more this way? Where do I put it? And that leads us to the second topic of chapter 5, the one we're actually going to focus on first, and then we'll come back to this. And that is, and I'm answering the two questions right now. First, and this is preview. I'm not even going to write this down. I just want to plant this seed in your mind. The answer to the two questions I just posed are, the magnitude of this, as we're all going to see, is effectively the area of that shape. So we're going to figure out what that area is. Now there's going to be some math associated with that, but it's nothing more than the area. So the answer to the magnitude is the area under the curve. The answer to the location is through the centroid of the shape. The center of gravity, if we're talking about something that has mass in a gravitational field like here on planet Earth, or center of mass if we don't have gravity, and guess what? Call it a centroid, call it a center of mass, call it a center of gravity, and they're exactly all the same thing anyway. It doesn't make any difference. We're not gonna get in the weeds on that terminology there. But the bottom line on that is, again, the magnitude here is the area of this, and the location is where's the centroid, the center of gravity of that shape right there. Because if we can figure out the center of gravity of that shape, that arrow has to pass through that center of gravity. Now what's also important about that too is all throughout the course, we have ignored the location of weights. In fact, for most problems, we've ignored weights altogether. We've said, hey, got this can crusher. If I pull up on the handle with 20 pounds, I get 118 out the back end of that. We saw that the other day, right? But nobody ever said anything about, hey, the handle itself weighs 6 pounds. Remember, DE weighs a pound. Remember, BC weighs, all that kind of stuff. We didn't do that. Why? Because we really weren't equipped to handle that. But we're moving in that direction. So let's even answer the question of how do we deal with weights. Kind of goes along with what we're talking about right here. When we know the weight of something, we already know the magnitude. What we don't know is where to go. The answer is it goes through, or I should say the force passes through the centroid of the shape. So it's incumbent upon us here in chapter 5 to figure out centroids. What do they mean? And most importantly, how do we figure them out? That's where we're heading right now. So now, when it comes to figuring them out, we've already done that in some cases. So for example, we have, until now, used the term or the word uniform. I'm looking for my pen, I don't know where to put it, doesn't matter. We've used the term uniform a number of times. If I had a uniform shape, we have said before that the weight of whatever that shape is passes through its geometric center. Why? Because that's where the centroid's at. That's where the center of gravity's at. So, for example, if I had, let's say we're working in 2D world, let's say I've got a tube that looks like this in 3D world, but I'm only looking at the front of that tube as this circle right here and this circle right here. And I want to know where's the centroid of that. Because this shape is uniform, it's geometrically uniform, then it shouldn't be a big leap of faith to realize that the centroid and the center of the circles are one and the same. The same goes for if I've got a square or a rectangle or anything like that. If I've got, let's say, a rectangle like this, and it truly is rectangular, then if I think about, well, where's the geometric center of this thing? Right smack in the middle of that, that's where the centroid's at. Now, we haven't talked about it yet, but what if I've got something, though, that isn't quite geometrically uniform like that? Let's say, for example, that I've got a mechanical element that is T-shaped, like what I'm showing right here. Now the question becomes, where's the centroid of that? Well, this one isn't quite as obvious anymore, okay? But we do know this much. All centroids, and you want to remember this, all centroids always exist on a line or a plane of symmetry if that exists. So in this case here, if we look at this T-shaped object, is there symmetry anywhere? Yes, of course. It's right through the center of this. Right? So I've got a plane of symmetry passing through here. I know at least this much. I know that the centroid of this is going to pass somewhere, or is going to exist somewhere on this line of symmetry. What I don't know is it there? Is it there? There? All these different pieces. So I know that it's here somewhere, but at this point, this stage of the game, I don't know where. Now this brings us to the notion of let's always listen to common sense, as we've talked about, and expectations. Folks, the centroid by definition, and I do not want to get in the weeds on this because this is just one of those things that's like, it's sort of abstract, but it's the idea that if you identify the centroid of shape, then all the moments made up by all the things surrounding that centroid, they all have to be the same, or they all have to add to 0. That's what it's all about. If you think about that, if that doesn't smack with the principle of moments and how that's going to help us out here, it's about to. Okay, it's going to. But having said that, you can also say, all right, well, if we're talking about a place where all the moments have to be the same about that point, then wouldn't it make sense that you could also view the centroid as being, all right, then that means that if I were to crunch all this down into one area where I'm taking all the mass and trying to focus it on one point, then that would also identify where my centroid is. And the answer to that is, yeah, exactly. But again, I don't want to get into the weeds of the analysis of that. I just want to keep that kind of high level, 30,000 foot, qualitative at best. All I'm saying is if you want to know where the centroid of a shape like this is, just imagine, and there's a reason I'm telling you this, by the way, just imagine that you took all the mass and kind of just tried to squeeze it all into one place. If I've got more mass up here than I've got down here, then I would think that the squeezed together mass is going to be closer to up here than it is down here, right? In that sense, we would expect the centroid to be somewhere up in this area, not down in this area, because this is not where the mass would all come together into a single point. Now, let's say that I've got a shape better than what I just drew right here. Hang tight. So let's say I've got a shape that looks like this. And I'm purposely drawing this because in a way that I want it to appear that this length here, this length here, this length here, this length here, this and this are all the same. Which means that there is a line of symmetry passing through this that goes like that. That's my symmetry line. Now, where's my centroid? Well, I know it's on this line of symmetry. If I squeezed all this stuff together, where would the mass kind of end up? You might say, well, if I squeeze it all together, maybe about where my finger is right there. But notice where my finger is, folks. My finger is not on the actual physical object. I'm saying that if I brought all this mass together, I might expect that my centroid might rest somewhere in that blue circle right there. But again, that's not on the physical piece. Question becomes, is that okay? Is that cool? The answer is yes. The centroid does not have to exist on the physical piece. Go back to this piece right here. If this represented the face of that tube right there, the centroid of this is smack in the middle of it. It's not resting on the piece either. So there's nothing wrong with the centroid not resting on the actual piece itself. But through all this, we get an idea, we get a sense of where we should expect the centroid to be in certain shapes, right? And we're going to, and why am I talking about that? Well, because we're about to take a look at a couple of techniques for how to mathematically calculate centroids. And folks, lean in on this one here. Hear what I'm saying. If there's ever once been an opportunity to make math mistakes in this course, here's where it comes in. We are going to see that our challenge in all of these is just getting the math right. And the easiest way to catch a math mistake is to, before you even go into a problem, ask yourself, where do you think the centroid is going to be? Where does common sense tell you it should be? And you're going to find that if you do that, and if you follow that idea, you will save yourself over and over again when there's a math mistake getting made, and it will get made. You will use that technique to find it before it finds you. And that's a very smart way of going about things. Now, I said that we're going to take a look at two different techniques for how to calculate these things. Let me let me get my notes together right here, and let me draw up a real simple shape here. Folks, the shape I've got drawn up here on the board, obviously a simple triangle, right? The question that we're going to address right now is if I saw that triangle, and I'm making up something here. Let's say that this triangle represented a 1/2 inch thick steel plate. All right, so the depth of this is a 1/2 inch going to the board. We're in 3D world right here, and this 1/2 inch thick steel plate has some kind of a height, some kind of a base, and I want to know. Let's say that 1/2 inch thick piece of steel, weighs 80 pounds. Let's say I want to know, where do I represent that 80 pounds? The answer is that 80 pounds is going to be a single force. Like all weights, it's going to be pointing towards the center of the earth, and it has to pass through the centroid of this shape. Or again, because we're talking about something that has actual mass and gravity associated with it, you could also call that the center of gravity, it's also the center of mass. You're just going to hear me say centroid over and over again because, folks, it's kind of a one phrase does it all kind of thing. So the question for us becomes then, where is the centroid? If I looked at this and said, let me back up on that. We're going to figure out where the centroid is, but before we do that, we would look at this and ask ourselves kind of where do we think it's going to be, right? So think about this, folks. And again, you got to visualize this. If this really was a triangular piece like this and I kind of squeeze all the mass down into a kind of a singular area, I don't think it would be a big stretch to say that the centroid probably should be somewhere in an area about here, right? That should resonate, that should make some common sense to you. So we know it's in here somewhere, what we don't know is where. So if this point right here represents the centroid of this shape, we need to have a technique that's going to allow us to determine analytically where that is. And how we're going to determine that is by specifying its coordinates. In other words, what's its value of x? What's its value of y? In fact, that value is going to be represented as a distance over from here to here. We're going to call this x bar. The bar is going to indicate to us that we're talking about a centroid there, folks. And this distance right here, we're going to call this y bar. That's going to be measured from the x-axis. Now, I just said something in that is brutally important. And folks, I'll say this a lot of times because it's that important. We've all got to hear it. When we're working with centroids, the most important thing we're going to do is always make our measurements from a common reference point. You pick it. You can pick any point you want, but all measurements must be made from the same common reference point. In this case here, the logical place to measure it from, for example, measuring x bar, the logical place would be, well, how far away is it from the y-axis? If I'm measuring y bar, the logical place is, well, how far away is that from the x-axis? So in that light, the x-axis and the y-axis become our common reference points. Everything now is going to be measured from those common reference points. What's important is to understand that when we're doing centroids, we have the right to put the axis wherever we want. You can, and you're going to find this out as you do these problems, you're going to find that moving the axis around can sometimes really help you make the math a ton easier. All right? And we learn that through experience, of course. But the point of that is wherever you move it to, which is your choice, that choice now becomes the common measurement base for everything, all right? Everything. Now you're probably thinking to yourself, man, you are really beating that dead horse there. I kind of got it after the third syllable. Oh, trust me, if you're going to make a math mistake, this is going to be where it's going to happen, all right? It's always in the measurements, okay? So trust me when I say this is a big deal. But all right, having said all that, I have a desire to figure out the x bar value and the y bar value so that I can specify the centroid for this shape right here. The question becomes, how? How in the heck are we going to do that? Well, here is where I'm going to introduce something to you where you got to take a little bit of a leap of faith, all right? And it goes like this. The answer to figuring out where the centroid is going to be driven by the principle of moments. The idea being here that if we view this, and I want you to visualize this and imagine this as a real object, like I said, a half-inch plate of steel or a half-inch piece of styrofoam or I don't know, whatever, a poorly cut chunk of bacon. It doesn't matter what it is. It's a real physical object. The principle of moments tells us that if we were to take this real object and let's say we were to swing it around the y-axis, then that real object, because of the fact that it's got weight, that real object would be able to impart a moment around the y-axis. In the same vein of thinking, if I took this real life thing here, this real life whatever, and I try to rotate it about the x-axis, that real life thing would also have the ability to cause a moment about the x-axis as well. Again, we only see this if we visualize this not as a drawing of blue ink on a whiteboard, but as a real life thing, all right? And it's easier to, I always felt it's easier to imagine it because we think of gravity, we understand gravity, and think about this. If this was a half-inch plate of steel, and I had that welded to some sort of a rod down here representing my x-axis, and I tip it over so that the weight is falling like this, then would that twist that rod that it's welded to or attached to? Of course. So therefore it's causing a moment. Now the principle of moments comes in and says this: whatever the moment would be that this object would create if we tried to rotate it about the y-axis. And I'm going to focus on the y-axis first here, folks. But if I try to rotate this about the y-axis, whatever moment this would create, according to the principle of moments, I would get the same moment if I were to cut this up into chunks, which I think is the question that you asked earlier on. What would happen if we separate this into pieces? Well, if I cut this up into chunks, and I looked at the moment caused by each chunk, the principle of moments tells me that whatever moment I get due to the individual pieces, it would have to be the same as I would get for the whole piece kept together. And the same thing goes for rotating this about the x-axis. If I think of the moment that this could create about the x-axis, this piece as a continuum would cause about the x-axis, then according to the principle of moments, if I were to chop this up into pieces and look at the moments due to the individual pieces and sum those moments up, I'd have to get the same thing. That's what the principle of moments tells us. And it's through that we're going to see a way now to actually figure out where these pieces are. And it goes like this. I'm going to erase this just temporarily, folks, but I do want you to remember, maybe I'll put it back in, that we said we think it's reasonable that the centroid is somewhere in this area that I've just drawn right here. Again, we don't know exactly where, but we think it's somewhere. So now, the way we're going to define this is by the principle of moments. If I contemplate the moment caused by this piece right here about the, let's go with the y-axis first. The moment about the y-axis. That moment, by definition, would be the centroid value x bar, which, just to remind you, that was the distance from the y-axis over to where the centroid was, multiplied by the force of this area. And here's the leap of faith I ask you to take. We have not heretofore thought about areas as forces. right? And we're really not technically thinking about areas as forces, but what we're contemplating is if something was a physical object with area, with mass, then it would have a force associated with that. So, by the definition of how we're going to define this moment, we're going to define this moment as being the x value of the centroid times the area of this entire shape. In other words, if we viewed the area as having a propensity to cause a force, and we multiplied that force by this distance here, the distance from the y-axis over to the centroid, x bar in other words, then that's going to cause a quantifiable measure of the moment that this would cause or create about the y-axis. That's the leap of faith I need you to take. But the principle of moments takes it a step further. The principle of moments says if we were to bust this all up into a bunch of pieces, that this would also then have to be the same as the sum of all the moments due to the little pieces, which we can write that here, folks. Let me just write this out this way, and then we'll explore on this one a little bit further. So that's going to be the sum over any index here where I could be just one piece, or it can be any number of pieces here, of the individual x sub i's times the differential area sub I. Uh-oh, a differential. We're going to the calculus world here. This will be, by the way, this is the only time in this entire course we're going to do anything at all with any kind or form of calculus. So what this means here, folks, is, again, and this is a representation of the principle of moments. I'm saying the moment that I get one way has to be the same as the sum of the moments I'm going to get some other way. That's the takeaway from this. And that's just plain old pure principle of moments. But it's going to start now with coming back over here and defining, and I'm going to get rid of this thing, it's just kind of bothering me, I don't want that there anymore, we'll put it back later. Of defining now these little differential pieces of area. And there's a couple of different ways we can do that. I'm going to actually shut the door, folks, give me a sec. Blah, blah, blah. So it's going to start with, we're going to define some little tiny differential area here, which I started to say a moment ago, and I don't know if I completed it. I could define it as a rectangle like this, with an aspect ratio with the length being vertical, or I could do it this way. It doesn't make a bit of difference. All right, it doesn't make a bit of difference. There's a mathematical advantage in one way or the other. But for now, I want to define this as this rectangle is, by definition, my differential area. This tiny little dimension right here is going to be some differential value in x. And this particular rectangle has to have a centroid. Right? The particular rectangle has to have a centroid. But like all rectangles, its centroid is going to exist right at its geometric center, which means there's going to be some value here, some distance from our common measurement point, in this case the y-axis. There's a distance from it over to this centroid, and this distance is what we're defining as x sub I. So now, with that said, let's expand the moment equation over here to now look at this from a differential perspective. So my moment about the y-axis is now written as an integral of all of the x times dA's. In other words, all these x sub i's times these dA's right here, I'm going to integrate those things. And if you look at how we would define dA, dA is like any other rectangle, folks. All rectangles, the area of a rectangle is nothing more than the base times the height, right? There's nothing new here. So dA, by definition, would have to be my base, which is dx, times my height. Now my height here, folks, my height here is some arbitrary value of y. I don't know that value yet, but what I'm eventually going to do is I'm going to figure out a definition of this curve as a function of y. But for now, it's just some arbitrary height along this y-axis here. So I can write that as y dy. So if that's the case, then when I come over here And by the way, I meant to mention this here, folks, but if you look at this integral right here, that is really a discrete version of this, or I'm sorry, a differential version of this discrete right here, so it's the same thing. So I can also rewrite this now as the integral of x times dA, which I've written here as y dx. So now, as I said a moment ago, what I got to do is I need to write a function for this height y right here as a function of x, which means I need to write an equation of this curve here as a function of x. But in this particular case, as we look at the curve right here, it's a straight line. It's linear. I mean, this is nothing but a linear straight line, and we know there's all kinds of different ways we can get about that. I'm kind of old school when it comes to that, so I always think the point slope form right here, so y is equal to mx plus b. So if I do the old, I want to write this value, or this function here, I want to write this as a function of x, right? That's my play. In this case here, y is equal to mx plus b, where m is going to be my slope. Right now, my slope here, of course, is the rise over the run. In this case here, I've got a negative slope, so I got negative h over b in this case here. So if I keep writing this out, I'm going to have negative hx over b, and then of course, not to confuse the terminology here, folks, this is just, again, this is just old algebra terminology. This b here is not meant to be the same as that b right there. What b is here is it's meant to be the y-intercept. In other words, where's the line cross the y-axis? The line here crosses the y-axis right there, where the value of y is equal to h. So my formula here simply becomes now h. So if I write this out, I can actually do a little factoring here. I see the h's can come out. So I could write this here, and I think I'm going to make this my final form, in that y is going to be equal to, I'm going to pull out a negative h from this. Y is equal to negative h times, in this case here, x over b, and in this case it'd be minus 1. So negative h times minus 1 give me positive h, so just like that. So now, folks, with that, now I have a function written for y. I can substitute that in over here into my equation that I'm writing. So let's play this out. So now I'm going to have the integral of x times y, which we've got here as minus h. You know, minus h is a constant. So I'm going to go ahead and pull that on out here, folks. So I'm going to have a minus h out here times x over b minus 1 dx. And as we look at the differential here, folks, everything now is in terms of x, which means we can solve for this one. We can solve for this here. All we need to do is we need to add in the limits of integration, right? So the limits of integration, in other words, what are my values of x from the low end to the high end? The low end value of x is 0. The high end value of x is b, the base, right? So I can integrate this now, or set my limits of integration as being from 0 to b, and all right, voila, now I got something that I can solve. So if I work on writing this out, writing out this integral here, I'm going to have the following. I'm going to have minus h times, I'm going to rewrite the integration here. So the integration of 0 to b of x squared over b minus x dx. And then, folks, if I go ahead and write that out, then I'm going to have minus h times now, so we integrate that, we're going to get x cubed over 3b. So x cubed over 3b, and that's going to be evaluated from b to 0. And then minus x, so that's going to be minus x squared over 2, also evaluated from b to 0. And if I continue working that out, I'm kind of running out of board space here, but I think we're going to be all right. This now becomes, I would have b cubed over 3b minus 0, so the 0 doesn't do anything. So b cubed over 3b, 2 of the b's are going to go away, so I'm going to be left with x squared over 3, or b squared over 3, sorry, said that wrong. So minus h times b squared over 3, and then here I'm going to have minus b squared over 2 minus 0, so no change there. So minus b squared over 2. And folks, the common denominator, and that's going to be 6. So here I would have, what am I going to have here? I'm going to have, so I'm going to have 2b squared minus 3b squared all over 6. So in that case here, this is going to write out, we'll have the final result of this to be, and I'm going to bring this back because I want to make sure we see what this is. This is the moment about y is going to end up being, after we solve the math on this, it's going to end up being h b squared all over 6. There we go. And it became positive. It became positive, by the way, folks, because again, the numerator here is going to have a 2 in it. This will have a 3. So 2 minus 3 is negative. So negative, negative becomes positive. So that's where we get this. So now, again, what was the point of all of that? Well, what we've got right now, folks, is we have a representation for the moment caused by the differential areas integrated over the entire shape. I know the moment that these areas create about this y-axis. How that helps me figure out, though, my x bar value is we come back up to this very important equation right here. The seminal equation of the whole thing is this. That same moment has got to be equal to x bar over a, which means I can now write this in the following way. X bar, the thing that I really want, I want the x value of my centroid. X bar is then going to be equal to, by definition, the moment about y divided by the area of the entire shape. Well, now let's think about that. The area of a triangle, at least as drawn right here, the area of this particular triangle is going to be nothing more than 1/2 the base times the height, right? That's just standard for any old triangle. So 1/2 BH. So if I write this out, I'm going to end up with then my expression for the moment about y, which we figured out using our integral right here, is hb squared over 6. So hb squared over 6 divided by the area, which we just got through saying for a triangle is the base times the height divided by 2, or 1/2 base height, right? So hb divided by 2. In this case here, folks, when you look at the stuff we got written up there in the upper right-hand corner of the whiteboard, we see that the h's are going to cancel. 1b is going to cancel out. And when I take 6 over 2, I'm going to end up with over 3. So this is going to end up looking like the following. It's going to turn out that the final answer on this thing is nothing more than b over 3. Saying that the centroid, which remember, we envisioned that it was going to exist somewhere in a circle about where I'm drawing my finger here, that at least the distance from the y-axis is going to be whatever the base is here, coming from this edge here, and this again, I cannot say this importantly enough, from this edge to that centroid is nothing more than 1/3 of whatever that base is. And if you think about that, folks, just kind of eyeballing it, that falls exactly where we thought it was going to be. Now, it shouldn't be any kind of a surprise to say, if I went through and repeated all that process right there, where now I'm going to try to figure out the y bar value measured from the x-axis right here. If you think about that, because of the nature of the triangle, you can imagine I just turned the triangle on its side, right? It shouldn't be any kind of a shock to anybody that the distance of this is going to be simply 1/3 of whatever the height is. So it's going to turn out, folks, that, and I don't want to erase that before we're done, let me just redraw this here. If I take a look at any triangle that is shaped like the one that I've got drawn over here, and I want to know where the centroid is, it's going to turn out that the centroid is always going to be, if this is the base, if this is the height over here, this distance from here to here, if I treat this as my y-axis, if I treat this as my x-axis, this distance here is always going to be base over 3, and this height right here is always going to be height over 3. And that tells me where the centroid of a triangle is going to be. And if you look at this, this is exactly right in the region that we thought it was going to be. So that technique right there gets us to the centroid. There's a couple of takeaways I want you to have here, folks, and no, we're not done seeing that. We're going to see it again. But the takeaway I want you to see right there, folks, at least for now, and let me back up and say to you all, I don't want you to invest much in that. That was a check mark. All right? I want you to see that is the technique we can use to find general centroids. Okay, we'll see it one more time, but don't get too caught up in that. But what I do want you to get caught up in is the idea that we did that by using a variant of the principle of moments. That is everything, folks. That is absolutely everything. Now, there's a lot up here. I'm about to erase it. And again, with the encouragement that we don't want to get too caught up in this, does anybody have any questions on that right there? Yes, fire away.
How do you find the A's HB over 2?
Say again for me.
How do you find the A's HB over 2?
Base times height, so the area of any triangle is its base times its height divided by 2. This is just standard. Does that take care of you?
Yeah.
Okay, good. Other questions, anybody on this? Cool, let me get rid of this. Throw one more up here. And trust me when I say I'm leading to something much better. Okay, folks. So now we got a shape sitting up here. Again, we can think of this shape as perhaps being some kind of a physical plate of steel, plate of aluminum, whatever. And we see how this thing is defined as certainly not a uniform shape of any kind right here. It's a quadrilateral. Height here 5, base here 5 as well. We see a line here with a slope. We're given the slope here 0.6. So emanating from 0 down here and ending up at 3, as you see over here. The slope here is 0.3, ending up there with a value in that case of y is equal to 6.5. So the goal of this particular problem is we want to figure out where the centroid is for this shape right here. Now, folks, once again, this is where it is so smart to, again, just kind of get a sense of where do we think it's going to be. I can tell you right now, a math mistake on this would be so easy to make, so common a mistake, and then all of a sudden you've got something that's telling you that, hey, the centroid is like over here, when in fact we all should be able to look at that and say, no, there's no way the centroid's over there. So where is it? Well, if we use that idea, take the shape and kind of condense it down, I feel really good about saying that the centroid is maybe somewhere in this region here that I'm using my red pen to draw. Maybe I don't really like that as much as I thought I did. Maybe it's more, I think I didn't quite go over far enough, so maybe it's more like in this region right here, somewhere in that area right there. That's where I think it's going to be. But I want to know. I want to figure out exactly where the centroid is. So let's do this. Let's first, we're going to go do the same technique we just did there, but let's go ahead first and write the equations for these lines. They're both linear. So in this case right here, if you think about the equation for this line right here, this equation for this line here would have to be y is equal to, once again, so it's linear, so use y equals mx plus b, where m is the slope. We're given the slope of 0.6, right? So y is equal to 0.6x. B in this case represents the y-intercept, which in this case is 0, so there's nothing there. So that right there is the entirety of the equation for that line. This line here is nothing more than y is equal to 0.6 times x. Up here, we're going to have y for this line here as being, again, the slope, which is given to us as 0.3, so 0.3x plus, in this case, the y-intercept, which the y-intercept here is going to be 5. And it doesn't hurt to look at the equation and ask, do we get the result we expect? If we were to plug in x is equal to 5 right here, 0.3 times 5 is 1.5, 1.5 plus 5 is 6.5, so it gives us exactly what we want. So we should be good with that. So now I want to use the exact same play that I've used before to figure out the centroid. I want to do one little thing though, folks. Since I think of this as the bottom line, I think of this as the top line, I'm gonna do a little nomenclature here just to make sure we know the difference between these. So I'm gonna call this one down here y sub b for y at the bottom, and I'm gonna call this one y sub t for y at the top. And I'm gonna go ahead and define now a little differential area within this. So I'm gonna define a dx as being a rectangle in like so, where just like before, this distance here is some, again, tiny dx value. This height right here is a little bit different. If you think about this height of this height here is going to be whatever the value of y is here minus the value of y right there. So that's going to be the height of this rectangle. So if I write my differential area out for this, which I think I'd like to use my black pen now to do that, my differential area as defined right here, dA is always going to be the rectangle, so dA. My differential area is going to therefore be the y value at the top, so y sub t, minus the y value at the bottom, so y sub b, times, in this case, dx. So now if I expand this out, we've already got expressions for yt and yb, so let's plug those in. So in this case here, this would be the same as 0.3x plus 5 minus yb, and yb here was minus 0.6x dx. And I can take that a step further and combine the x terms here. So my final representation of this would be 5 minus 0.3x. So I'm going to have 5 minus 0.3x dx, and that is my representation now of dA. Now, what I don't have on this shape right here, is a, let me say it differently. There's a couple of ways I can go about getting the area of this shape. I can figure out the area kind of by doing a little geometric playing around here, which is fine, or I could just integrate the area, right? So, integrate the dAs. So if I want to get the area, because I know I'm going to need the area eventually, so the area of my shape now is the integrals of all the dAs. And that's all done over x's, so I need to, in this case here, set my limits of integration for the high end and the low end of x. So the low end is 0 again, the high end being this spot right here is 5. So 0 to 5, Now this, I'm going to have 5 minus 0.3x dx, which is the same as, let's see here folks, let me play this all out. So it's the integral from 0 to 5 of 5x dx minus the integral of 0 to 5 of 0.3x dx. And if I plug in all those things here, folks, let's see here. So this is going to be, let me see. Yeah, I'm sorry, I added an x in here. I knew something was wrong. I added an x and I didn't mean to. 5 minus 0.3x. So if I integrate this down here, I'm going to have 5x evaluated from 5 to 0 minus, actually this is going to become now a plus. So let's see here. Nope, I did double on the negative, sorry, screwed that up. So this still is a minus. In this case here, 0.3 x squared over 2, that's also evaluated from 0 to 5. And folks, when I get done with that, I'm going to end up with the following. I'm going to have 5 times 5, which is 25, minus 0.3, so x squared here would be 25, so 0.3 times 25 divided by 2. Let me just write that out. So minus 0.3 times 25 divided by 2. And when I get done with all that, folks, I'm going to end up with, plugging this in and crank this all out, my area is going to be 21.25 square units. By the way, the units are just the units. They're inches, meters, feet, whatever you want to be. It doesn't matter. I'm going to write that over here separately, so I want to keep track of this. So area is equal to 21.25 square units. Now, going back to our fundamental definition, I want to be able to get the centroid. We are reminded that the moment about the y-axis is given by the centroid times the area, but it's also given by the integration of all the xdAs. Same equation we saw previously. And I've got a representation for dA up here, so let me plug that in and crank that out. So this is going to be equal then to the integral from 0 to 5 of x times dA is written over here, 5 minus 0.3x dx. And folks, I'll save you all the hassle of playing that all out. When we get done integrating that, we're of course going to end up with, let's see here folks, this of course would be 5x squared over 2 minus 0.3x cubed over 3, evaluate from 0 to 5. When I get done with all that, maybe I better write that part out. So it's going to be, we're going to end up with 62.5 minus 12.5 on the evaluation, which leads us to simply 50. So now, and again, I'm skipping the math on this, assuming you don't really need to see the math or you don't want to see the math, but if you do, let me know. So now, folks, with that, now we know that the moment about y is equal to 50, and according to this equation right here, x bar is by definition equal to the moment about y divided by the area, which is going to be the 50 that we just calculated, divided by the area that we calculated earlier, 21.25. And folks, if you plug that in and crank that all out, we're going to end up with x bar value of 2.35 units. So right now, we know that our x bar value is equal to 2.35. And again, same technique, nothing new. So far, so good. Questions, anybody so far? All right, now, I want to quickly, and again, I don't want to get too invested in this, but I want to show you how we're going to do the moment about the x-axis right now. So, let's see here, folks. I'm going to keep some stuff. Yeah, that part I'm going to keep up there. So I'm going to keep my rectangles defined in the exact same way. And I'm going to also note that my moment about the x-axis in this case is by definition y bar times the area, which would be then, let's see here, that's the same as all of my integrals of y sub I, or the y to the centroid here, times the dA's, so nothing new in the way we're writing that out. The difference here, folks, is that now we are coming up with a distance from the x-axis up to the centroid of this piece right here. So remember, the centroid is in the middle of our rectangle. So this distance right here is the individual, I'm going to call this y sub i's, just to make clarity on this. So this is going to be my individual y sub I right here. So very importantly, where is that? Well, if you think about this, folks, this distance right here would have to be the same as the average between this height here and this height right here, right? So if that's what that is, I need to cap this red pen here, give me a sec. If that's what that is, then, oh, you know what, folks? Yeah, stick with it the way it is. So y sub I here is going to be defined, again, as the average between this height and this height right here. So this height here we already know is going to be 0.3x plus 5. So 0.3x plus 5. And average, of course, we're going to sum the two components and divide by 2. So plus this height right here, which is 0.6x. And that's going to be divided by 2. So when I plug all that stuff in and crank all that stuff out, I'm going to have 5 divided by 2, which is 2.5. And then 0.3 plus 0.6 is 0.9. Divided by 2, that's going to be 0.45. So plus 0.45x. That's what the y sub I is here, folks. So now, with all of that said, I can come back over here and now I can write this accordingly. This is now going to be the integral of my y sub i's, which I got here as 2.5 plus 0.45x times dA, which I've already written up over here as 5 minus 0.3x dx. And obviously I'm going to need to multiply all those terms out. By the way, this is all in x, so our limits of integration will remain the limits on x, so 0.5. So okay, what do I got here? I got 2.5 times 5. Let's work this out. So 2.5 times 5 is 12.5. So I'm going to have the integral here, 0 to 5, of 12.5. Let's see. So 0.45x times 5 minus 0.3x times 2.5. When you plug that in and crank that all out, ladies and gentlemen, you're going to end up with plus 1.5x. And then the final terms down here, 0.45x times minus 0.3x. Plug that in and crank that out, you're going to end up with minus 0.135x squared. All of that times dx, and now we can integrate that out. So work the integration out here, so we're going to have 12.5x plus 1.5x squared over 2 minus 0.135x cubed over 3, all evaluated from 0 to 5. Folks, when we get done with that, we are going to end up with the following. We're going to have the following terms after the integration. Wow, that hurts right out. I keep thinking I don't need to write it out. I really should. So I got 12.5x plus 1.5x squared over 2 minus 0.135x cubed over 3. All of this evaluated from 5 to 0. Folks, when you plug that all in and crank that all out, we're going to end up with the following. We're going to end up here now with that moment about the x-axis being 75.625. So now, if you think about this, we know the moment about the y-axis. If I want to get my value of y bar using this equation right here, I got y bar is equal to my moment about the x-axis, that is figured out, divided by the area. So I'm going to have 75.625 divided by the area, which I calculated a long time ago at 21.25. And folks, that's going to end up being 3.56. So now I know that my y bar, I'm going to write this up over here, y bar is equal to 3.56. And folks, let's just look at these numbers right here. Look at these. 2.35, so if this is 5 right here, then 2.35 is really close to about the halfway point, so right about where my finger is. Y bar is 3.56, so if this is 5 here, then 3.56 from the x-axis would be about 3/5 of the way up, so maybe about right there. If I bring these things together, look at, my centroid ended up being right in the zone I thought it was going to be. It makes perfect sense that that's where it is. So now, we have seen that technique from both ends. I'm looking across the room right now, and I'm not seeing a lot of people with this like, man, this looks like this is gonna be a lot of fun look on your face. I'm seeing a lot of heads going, oh man, no. All right, here's the good news. You just saw the last of anything having to do with a calculus-based technique in this course. We will never see that again. The logical question, even though I just said we will never see that again, I'll think of the question, but does that include the final exam? You will never see that again. In fact, hear me when I say this. If anybody solves a centroid problem on an exam using that technique, I'm going to purposely fail you, just to bring you back and make you do this all again. Do not ever do anything like this, folks. I want to show you a better way. So check this out. While the technique that we just did right there, and let me be clear, the technique that we just did right there would let me calculate centroids for all kinds of things. Let's say I had something where there's some sort of a weird function in x and another function in x that does this. I don't know, let's say it's a shape like this right here, and I want to know the centroid of that shape right there. I just showed you a technique where I could figure out where the centroid of that shape is right there, right? We can do that. Here's the question for you, folks. In your careers that are about to ensue, how many of you think you're going to run into very many shapes like that in your career? If you're thinking a lot, you're probably wrong. You might, I mean, certain industries maybe, but most everything we do, folks, is not made up of shapes like this. It's made of common shapes, rectangles. When we drill a hole in something, that hole is typically circular, right? If I take a rectangle and I cut a straight line off it, I just lopped off a triangular piece. There's so much of what we do that's just based on common shapes. Now I want to tell you up front, in your textbook and in any statics textbook that's ever been written, there will be an appendix at the back of the book that's going to show you the centroid locations for common shapes. The triangle one that we did at the beginning right there, folks, it was already in the back of your book. It shows you that for a triangular shape like what I just drew right there, the centroid is 1/3 the base, 1/3 the height. It's that. But we need to see where that comes from, right? But if you think about this, most of the things we're ever going to do in our careers having to do with stuff like we're seeing right now is going to be done on common shapes, or importantly, a composite of common shapes. You take a look at this thing right here, and let me erase this stuff here, folks, before we go any further, before I erase it. Does anybody have any questions about this? Good. So goodbye, we never see that again. Don't gotta worry about that, yay. Let's go back to our original shape. So if you look at that original shape right there, folks, if I were to say to you right now, let's say we're working in some sort of environment, you're working for me, and I say, hey, I need you to go take a chunk of aluminum and make me a shape that looks like that, ask yourself, how would you do it? I mean, what would be your approach for how you would do that? The answer is, well, there's a couple different ways you might think about it. You might look at this and say, well, you know, I could take a piece of aluminum like this, a full rectangular plate of aluminum, and merely cut off this triangle up here, cut off this triangle down here, and what I'm left with is my shape. 100% right, you could certainly do that. You could also say, well, I could also start with a rectangle of aluminum, like maybe there's a rectangle of aluminum right here, and I've already got some triangular pieces cut out like that one and that one right there, and maybe I can just join those three pieces together and boom, I've got the shape. That'll also get you there. But the point that I'm trying to make, folks, is this. That shape right there is something that we can readily make out of a combination, and a lot of different combinations of common shapes, rectangles, triangles, we get there, right? So is there a way we can leverage that? Is there a way that we can look at this and say, well, I can figure out the centroid by taking account of all the centroids of all those common shapes? The answer is yes. The question becomes, well, what's the methodology? How do we get there? But you had a question, fire away.
Just looking at it here, if you go from one corner to the other, you make two triangles, and you find the centroid of those two triangles.
Exactly. And your point, very well taken, is there's a multiplicity of ways we can get there. And to your point, you could also do it by just looking at a couple of triangles, right? Readily doable. But I look at this and I say, all right, again, there's many ways I can go about it. Like, for example, this shape right here, the one that I want to make, I could see that as perhaps starting with a rectangle. So let me show you the rectangle I'm thinking about. So let's say I take a rectangle that's of that shape right there, so that this down here is the same as this space down here. And to this rectangle, which ends right there, I'm going to add to it a triangle on top, like that. I'm going to add a triangle on top to get this piece up here. But from down here, I'm going to subtract. I'm going to take away, I'm going to cut away a triangle like this and get rid of this piece here. So I'm going to cut away a triangle that looks like this. And that is a way, again, now I think there were up to 4 different ways we've contemplated of how we could make this shape right here. We can do it by, again, start with a rectangle, add a triangle to it, subtract a triangle down here, voila, got the shape. So here's what we're going to do. To do the centroid of this, I'm going to contemplate the centroid of this as being a function of the centroids of these common shapes. And let's be clear, where's the centroid of the rectangle? Answer, geometric center. Where's the centroid of this triangle up here? Well, it's going to be 1/3 of this distance here away from this line, so 1/3 back and 1/3 of the height, so right about there. Where's this one going to be? Again, 1/3 of the base back from the flat edge, 1/3 of the height from this flat edge up here, so right about there. We know where those centroids are going to be. So here's the technique we're going to use, and I want to keep these up here because we want to reference those again. The technique, and just like I said to you guys a moment ago, when we were looking at the integration technique, I said that was a checkbox. In other words, I needed you to see it. You've been exposed to it. But now what I'm about to show you is this is our way. This is the method we're all going to get really good at. And it's done by simply drawing a table. The table, I'm going to build it out that I'm drawing right now, folks. Get this in your notes, because every table that we're going to do for centroids will look exactly the same. So the table that you have right there, folks, that is the one I want you to make sure that you memorialize that in whatever way you want to memorialize it. This is the table we're going to draw, and it's always going to have these 6 columns that you see right here. The leftmost column is going to be a reference to what shape we're talking about. I'll come back to that in just a minute. The next column, the one to the immediate right of that, is going to be the area of that individual shape. Then we'll have the x value of the centroid of that particular shape. We'll have the product of whatever you have here times whatever you have here is going to go there. We're going to look at the y value of the centroid of the individual shape, and this is going to be the product of this value here times this value back here. Now, the reference, we got to go back over here to these shapes. I want to know the centroid for this thing right here, but I've already said I can build this out of 3 common shapes. I need to give these 3 shapes a name. The easiest way to do that, folks, is just give it a number. So, for example, let's call this shape here, let's call this one shape 1. Let's call this one shape 2. We'll call this one down here shape 3. And then over in my table, I'm going to reference those shapes. But I'm going to do something here that is very, very, very important. I have shape 1, which is my rectangle. Shape 2, the triangle over there in the upper right-hand corner of the board. And then shape 3 down here. But on shape 3, I'm going to add in a negative sign. Somebody tell me, why did I do that? What are you thinking?
Getting rid of area.
Exactly. Exactly. Shape 3 is not an area that's being added to the shape. It's an area that's being subtracted from one of these shapes here. And that, folks, is a critically important thing. Failure to make this to carry that negative thing through is going to cause math errors. So we want to do whatever we have to do to remind ourselves that, hey, we're taking this area away. The best way to do it, put a negative in front of that there, and then that'll help remind you to carry that through. Now, let's take this one piece at a time. I want to come back over to our original shapes, and I want to put some numbers on them in terms of dimensions. So remember, the shape that you see right here, folks, is meant to be this square here going all the way up to the height of 5 and over to this with a base of 5. So this has a height of 5 and a base of 5. Now this one over here has the same base of 5, but the height we have right here, according to our line, was 0.6x. So the height here is going to be 3. So we'll put that in. And then over here, and here's where we have to be really, really careful, folks. So this base right here, this is going to sit on top of this rectangle. So the base is still 5, but what's the height of this right here? Well, if you look at it, this point right here, we represented earlier on as 6.5, right? But the height of the square coming up, which stops about where my hand is, was 5. So if this is 5 here, in other words, y is equal to 5 up here, and this is 6.5 up here, then the difference between those is 6.5 minus 5. So my height of this rectangle over here is 1.5. But now, having said that, let's come back over and let's take a look at our table. I think I'll use my blue pen here. So shape 1, the square, 5 by 5, the area. So the area of the square in this case is going to be 5 times 5, simply going to be 25. Now, let's talk about its x sub I value. Remember, and you heard me say this earlier on, the critically important thing to always remember is every distance must be measured from a common reference. The reference we're using is the y-axis for these kinds of measurements, the x-axis for these kinds of measurements, right? So if you think about where's the centroid of this shape, we know it's in the geometric center, right? The distance from the y-axis over to that geometric center is half this 5, so that distance is merely going to be 2.5. So if I plug in a 2.5 here, and then I know that this is nothing more than the product of these two numbers, so 25 times 2.5 is 62.5. And then my y sub I, which is going to be a measure from the y-axis up to the centroid of this shape, but this actually rests on the y-axis, so it's also 2.5. So let's go here. So 2.5 on this, and this is the product of 2.5 times a sub I, which is also 62.5. And just like that, we got the first row of our table filled in. Let me pause. I want to make sure, does everybody see where these things come from, where these numbers come from? Cool. Now let's do the second part over there. So part 2, which we identified as this triangle over here. So this triangle, the area of the triangle is always 1/2 its base times its height, right? Base 5, height 1.5, so 1.5 times 5 is 7.5, half of that 3.75. So the area of this is 3.75. And now we have to be really careful with specifying where is the x sub I value. So let me come over to this triangle again. And I'm going to take this triangle up here, and I'm going to blow it up big so we all can see. Oops, that's a little too big. I want to blow that up a little bit bigger so we all can see it. So here's that triangle. We know the base of this thing is 5, right? We know that the centroid of a triangle of this shape, the x value of that centroid is 1/3 of this base, right? So this distance from here, the flat edge, to here is 1/3 of that, or in other words, wherever the centroid of this is, this right here is 5/3. But, oh, think about how easy it would be right now to go over here and say, got it, this is 5/3. No, it's not, because we make all measurements from the same reference. The reference is the y-axis. So we're not interested in this distance right here, even though this tells us where the centroid is. We're interested in the distance from here over to that centroid. So 2 times 5/3, 10/3, 3.33333. So there's the value that goes into our table. And again, it's because we make all measurements from the same reference, the y-axis. So from here over to here is 2/3 of the base, or 2 times 5/3 for this one. Now, going back to our table, same play here, folks. Xi, Ai, so 3.75 times 3.333 gets us to 12.5. Now I need my y value. And again, super careful here. We have to measure, going back over here, we're talking about a triangle here. I'm just going to put it in like that. We're talking about a location here that's going to be 1/3 of this distance right here. So 1/3 of 1.5 is 0.5, but I got to make my measurements from the same common reference. So from this common reference, just to get to the base, how far was it from the x-axis just to get to that base right there? 5. So just to get from here to the base was 5, and then my centroid is another 1/3 of this distance here, so 5 plus 1/3 of that, 0.5. So 5.5 is what's going to go in over here. Now, this column is again y sub I times a sub I, so 5.5 times 3.75. Plug that in over here, I'm going to end up with 20.625 in that column. Ask questions, folks. If you're not seeing it, if you're not clear, don't wait. Yeah, fire away.
Where does the 5.5 come in for?
Okay, perfect. So let's be clear. We're talking about this triangle here, right? And we know that the centroid of this is 1/3 the distance back here and 1/3 this height here. I'm probably a little low on that, but 1/3 this height right here, right? So if you think about it, 1/3 of this height here, since we know, going way over here, that this height here was 1.5, then that means this distance from this edge here up to here is 1/3 of that, 0.5, right? But I had to go from here, all my measurements come from the x-axis, I had to go up 5 just to get there. So 5 plus the 0.5. Thank you for asking that, because I think that's a hang-up for more folks in here than they're willing to admit. We all good on that one, folks? Okay, all right, so now we're down to this one here, area number 3. Same as before, this is a triangle, so look at it, folks. The area of the triangle is going to be 1/2 the base times the height. Base times height is 15, 1/2 that's 7.5, right? But this is a negative area. So I'm going to write into this here negative 7.5. It's a negative area. Now, let's do the same thing. Where's its x bar value? So just so we're all clear too, we're talking about a triangle that's being cut out that's right here. The thing I'm drawing in red, we're cutting this triangle out. So where's its x-axis, or I'm sorry, the x component of its centroid? Well, once again, if we look at this triangle, the centroid is 1/3 of the base away from the flat edge, but 2/3 from the y-axis. And it's got the same base of 5, so it's the same 3.33 again for its x sub I value. So I'll plug in the same 3.33. And if I multiply 3.33 times negative 7.5, we are just doing the math as it's presented to us. 3.33 times negative 7.5, that's going to get us to minus 25. Now I need the y value. So in this case here, the y value of the centroid of this piece here is going to be 1/3 of its height. The height here is 3, right? The height in this triangle is 3. 1/3 of that height is simply 1. So I'll come over here plug in 1. But now this product here, y sub I times a sub I is 1 times negative 7.5, so minus 7.5. And folks, you're about to see the beauty of this technique. Before I get there, are we good with these numbers? And just so we all know, we're going to see this several times, so you know we'll fill in some gaps. But y'all see where it's come from right now. Sweet. All right. So once you've got the shapes plugged in, here's the play. What you want to do is you want to add up the area column. You want to sum that column. You want to sum the product column there and sum the product column over here. We're going to do nothing more than add these things up. So I'm going to have 25 plus 3.75, so 28.75 minus 7.5. That's going to give me an area of 21.25. And folks, when we calculated the area before using the integration technique, we got the area as 21.25. So it's the same area. No surprise there. I would have been worried if it wasn't. When I add up these here, I'm going to add 62.5 plus 12.5, that's going to get me to what? 75, right? 75 minus 25, that's going to get me to 50. Here, 62.5 plus another 20.625, I'm up to what? 83 point some odd, and then minus 7.5. When I add all those guys up, I'm going to end up with 75.625. But now, very importantly, we go back to definitions that were no different than what we had back when we were doing the integration version. The only difference here is we're not doing differentials, we're doing discrete pieces, right? So in this case here, know this. For every time that we ever use this table right here, every time we ever use this table, the x bar value of the centroid will always be the sum of the x sub I, a sub i's. In other words, the sum of this column right here divided by the sum of the areas, or simply the area. And in this case here, ladies and gentlemen, my sum of my x sub I, a sub i's was 50. The area was 21.25. 50 divided by 21.25 is 2.35, which is exactly what we got before. You already know how this is going to end. Y bar, that's the sum of this column over here. The y sub i's times the a sub i's divided by the area. In this case, 75.625 divided by 21.25. Plug it in, crank it out. 3.56. We got the exact same area. I'm sorry, the exact same components of the centroid that we got when we did the integration technique. But ladies and gentlemen, please look at that table right there. I doubt there's a single person in this room that would argue with me when I say that is a hell of a lot easier than doing the differential technique. And because most of what we do is based on common shapes, this is a no-brainer. This is the one we want to get very good at. And folks, we're going to see more of this, but I want to just plant a seed. What if now we had this shape like this, and we said, okay, but now I want you to take this shape and I want you to cut a big circle out of it right here. Now where'd the centroid go, right? So how do we deal with that? Well, now we're doing the exact same thing. We're still building this shape out of these three pieces right here, but we're going to subtract a fourth piece out of it. We're going to take a circle out of that. Now we got a fourth piece over in our table, and we figure out with that centroid all day long. I challenge you to figure out how to do that with an integration technique. You can't do it. It would have to be something numeric. That right there, folks, is the thing we're going to get good at. Does anybody have any questions on that before we call it a day? Cool, let's call it a day. See you guys all, today's Thursday? Yeah, see you guys on Monday.